Recording. Okay.
Yeah. Okay. Perfect.
All right. So this meeting is about the. Let me share the screen real quick. Screen number 2. Let me know if you see my screen.
Yes.
Okay. So this meeting is about us covering the modeling forward kinematics of snake robot. The second group assignment. So as we were talking about, so we're supposed to cover the Newport key robot or the transbronchial biopsy catheter using the references from Seaman and Webster, which we have them here in the PDF.
Yep.
So the first problem set, it states that you got to use equation 1 through 3 from reference 2, which is Webster.
Yep.
So if we go to Webster, which is the design and kinematics,
Yep.
equation number 1 is this transformation matrix, which uses the rotation matrix through z-axis of phi, and then rotation matrix of y-axis using theta. And these two are known matrices except for P, which is the one right here using R for the first time.
So let's. I want to pause here for a second. If P, I mean, I'm just thinking we're recording, but I'm thinking here, if P is 0 and theta is 90 degrees, then that will be just a normal translation from the z-axis to the y-axis, correct?
That is correct.
Yeah. Yeah. Okay.
So problem set 1. Let me bring it up again. So I guess we're just supposed to like to create this, and that's it.
So follow derive equation 1 to 3 of reference 2. So when he says derive the equation, derive it from where? I mean,
from this. So I guess we're supposed to multiply this and get the final transformation matrix. And if it says from 1 through 3, it means that, well, this is 1. Where's 2? So this is 3. So yeah, exactly. We're supposed to get this matrix out of MATLAB, I guess. And then, oh, 2 is right here, is below.
So 2. So where did 2 come from?
So it's F.
DH axis. So are we, the resulting DH table is given in table 2. So where is the DH table?
Oh, it's
yes,
here.
I opened it, yes. So it looks like if we just use the DH table and do the normal transformation using the DH table as we're supposed to, we should get to the same result of equation 3, correct?
That is correct.
So if we just plug in the numbers of the DH table and use the DH method, we should get to that. So that's something we can try in MATLAB and see what we get.
Right. That should be the appropriate way, and that will give us. That will be problem 1. So let me write that down.
Okay, and we can both. I believe both of us need to try that, everyone separately, And then when we regroup, we see what we find out.
Definitely, and I can write this down in the discussion once we're finished here. So
Okay.
we're gonna do the DH table in MATLAB, and see that we get the same results
As equation 3.
Same results as equation 3. Okay, and then so if we do that, then we go to problem number 2, which is derive equation 1 through 4 of reference 1 to apply the concept the length of the I backbone on the angle of the end disc relative to the base disc. It does not depend on the shape of the backbone. The equation 1 through 4 will also give them how much should each wire be pushed from the snake to have the specific posture.
So equation 1 through 4, we have to open the other article, right?
Yeah, so reference 2 would be
the Seaman one.
Reference 1. So Seaman is reference 1. Let me go up. So Nabil Seaman. So high dexterity snake-like robot. And then there should be an equation 1 here. I did upload this file to the group files.
Okay, so this file, and then I had the other one uploaded too, which is the one we were looking at.
Okay. I see figures and procedures, but I don't see an equation number 1.
I don't know. Let me open again because I don't know if this is this the right one. Okay. Let's see here. I'm seeing what we, because I don't think that's the right one. There is another one, I believe, and I have it in there. So the continuum robot with follow the leader motion, I think that's the one which is the other reference. The first reference was design and kinematic modeling, which is the one, the Webster. The continuum robot with follow the leader.
That's the official robot we should be modeling, but reference 1 is let me. So reference 1 is Seaman, and Seaman is not on the continuum robot file.
You are right. You are right. But somebody was saying in the discussion group that Seaman is not correct anyway. It should be something else, but I'm not sure. Okay, let's go back. Let me check here something. So go back to the assignment, go back to the discussion group. Like reference one paper should be, which I don't know if that, yeah. Yeah, vector system. Okay, so it,
Okay, so we didn't have this paper before, so let me.
yeah. Does it open it, or can you download the whole? Yes. Yeah, I'm opening. Yeah, I opened it too. Are you saving it in the group?
Yep, that's what I'm gonna do now.
Okay. I'm looking for equation 1.
Yep, it's there now.
Okay. So equation 1, yeah, is on page 354, which is page 5, basically page 5 of the, at the end of page 5 is equation 1.
Okay, let me open that one.
The position and orientation of the end disk relative to the back base disk is characterized by two angles, theta L and I don't know, epsilon, I think, or I don't know what this symbol. The angle epsilon I1, 2, 3 are related to, according to equation 1. Okay. Yeah, right here. So it's showing here that the relationship, but then you've got beta, so division angle beta equal 2 pi divided by n. So beta is basically 2 pi divided by the number of links.
Where are you at, Ram?
Just where you were.
Okay.
And if you look above, like a few lines above in the description, beta, it tells you what beta is. Yeah, it's right here.
Oh.
You don't need to scroll, yes. So that's how you, number of secondary. So are we, so the first question, are we looking at, because when I read in the original paper, it looks like it's saying that the snake robot is made of 3 sections, and each section has a number of links in it. Are we doing it this way, or we are doing each link by itself as separately?
I still believe we gotta do each link by itself, and then R and phi will be the limit, the size of each link, I believe.
The what, sorry, of each link?
The R will define the length or the end position of each link.
Correct.
So I guess when we do the transformation matrix and we add, I don't know, if we change the value of R on the first document, where is it?
That's the first document here.
Yeah, here. Oh, it's actually K. So I guess we should start by playing with this in MATLAB and see what we get.
I agree with you. I just need to understand why is the GH table 4 links, and are we just I'm just trying to understand if we're doing, actually it's 5 links. So where are these 5 links coming from?
Well, when you read the assignment, where is it? It actually tells you that you're gonna map for this robot, the scatter enhanced by multi-section continuum robot, using the same equations from these two. So
Yes.
it means that we're still talking about a 6-section robot such as this one.
Yep. So if it's 6 section, are we thinking 5 links and the 6th is just the end effector?
Yes, that's what I believe too.
Yes, because once you brought that picture, I thought that's where you were going with that. So let's go back to the assignment then. So the first step, we're going to do the robot. We're going to do the GH parameters, get the transformation from the base to the last link, and then after this, we want to prove, we're going to the equation that you just showed, and we're going to prove that the length of the 5th or 6th or 7th backbone depends on the angle of the end disk relative to the base disk, and it does not depend on the shape of the backbone. And then the equation 1 to 4 will also give how much should each wire be pushed for the snake. Okay, so this part I still need to read to understand it. And then the third thing is use the following dimensions, r equal 1.5 in relation to reference 1, and draw a graph showing the motion of the robot by varying the pushing length of each wire. Assume the length of the primary backbone is 10 millimeters. Okay.
So when he says primary backbone, is it the base link or what?
That's what I'm thinking. That's what I... Yeah, maybe we need to go back to the original paper again.
Oh, there you go. It has it on the drawing. Let me share again. It says it right here. So it's pointing the wire of the 6th section, which is the white wire here, the 4th section black. So each section controls a different wire.
Correct.
And then the backbone, where is it? Here. So the backbone is this wire right here.
Which goes through the whole distance.
Right.
It goes through all the sections, 1 through 5 or 1 through 6.
Yep.
Okay.
So, but every cable goes through every section, right or not?
But every cable, no, because every cable pulls a different section. So wire of fourth section goes from the base all the way to the fourth section.
Oh, got it. Got it.
Now the wire for sixth section, the only thing that's confusing me is what's the difference between the wire for the sixth section and the backbone, because the wire for the sixth section seems to go through the whole thing.
Yeah, I think the backbone is exactly what it says. It's kind of what holds the whole
Yes.
robot together.
Yeah.
And then the wire for the sixth section is the wire that makes it move.
Makes the last section move.
Right. So it's kind of one wire for structural and the other wire for movement.
Yeah. So it looks like they're.
Go ahead.
I think I see what they're doing here. So there is a wire for the second section, but there is no wire for the first. And then there is a wire for the fourth, but nothing for the third. And a wire for the sixth, but nothing for the fifth.
Where do you get that?
Because I'm just looking at it here, I don't see the wires in it's just showing only those three wires. So I'm assuming, I don't know.
Oh, because it's a projection out of this section only.
Ah, okay. Okay. I see what you're saying. But if it's out of this section only, then where is the wire for the fifth section? Why is it not showing it? I don't get it.
Yeah, you're right. Why isn't it?
Yeah, why is it only showing those three wires?
No 3 or 5 section wires showing here.
Yes, and that's I'm just wondering why. I mean, I think we just need to read more the paper and try to get through those steps.
Let me see if there's something else here.
Backbone tube, wire guides, the wire guides. Figure on the push-pull wires for the second, fourth, sixth bending sections. The wire guides for the sixth section, which is on the bending plane, is fixed the distal end of the row. The other wire guides for are fixed at the distal end of each section. The wire guides for first, third, and fifth bending sections are aligned in the same way on the other side. Ah, so they're there, but they're symmetric. So
right.
Yeah. Okay, so that makes more sense now. I just didn't know. I wanted to. Okay, so it's the same thing, but it's on the other side of the robot.
And the 6 bending sections can be manipulated independently. The wire guides are aligned with the rigid portions of the backbone by using the fixing pins. The fixing pins have length of. So fixing pin. What is the fixing pin? Okay. Oh, here. So this is the fixing pin backbone. So the backbone is just, it doesn't move. It's just a flexible cable that holds all together.
Yep.
Okay. The wire guide. So that's the path of the wire.
Mm-hmm.
Eyelet, which is where the
wire goes through.
Wire goes through. Okay. Eyelet.
Because he has an eyelet here in front of the second section wire that goes all the way to the second
Right.
section. So this is it's just a hole where the wire goes through.
So fixing pin. Well, I don't understand what the fixing pin is. Let's go again.
Let's read that part again, yes. The wire guides are aligned with the rigid portions. The wire
So the wire guides are aligned with the rigid portions of the backbone by using the fixing pins. So it's an alignment.
So it looks to me like the wire guide sort of needs to be anchored in certain locations.
Okay.
And it's connected in those locations to the backbone. But then it just allows to, so this way, but if it's connected in certain locations, then how does it pull or push? I don't get that. It should be free to move. Unless,
Okay. So the fixing pins. So I think I get it. So in order for the robot, so they don't say this robot can. So like the sections, the rotating sections, they don't say at any moment that they can get together or separate more. It doesn't do that. So I get the fixing pins. It's what's holding them like at the same width all the time. I think that's what makes sense for me.
yeah, I see what you mean. So you're saying that it can only bend,
Right.
but it cannot go inside. The links don't go inside each other, and that's what the fixing pin does. It doesn't allow the links to go into each other, right?
That is what I think, because it also says there's the fixing pins have the length of 0.8 millimeter with the diameter of 2.
And define both the longitudinal and circumferential position of the wire guide for the rigid, so that bending moments are applied only at the rigid portions to in-plane direction. Bending moments are applied only.
I think that is what it is.
Yeah. So what we can do is, I'm thinking now that we have an idea of what we want to do. Do you want to go ahead and each one of us go through the whole exercise, and then we can regroup again?
Let's do that, yeah. So I guess vector style. This one we're not going to use.
Okay. So I think we know what we're going to do.
Yeah, the new paper, the one that for reference 1, is way complex.
The one for the ith section, right?
Right.
So I think we'll just do what we can. We focus on the first part of it, and we try to do the second part as much as we can. And then we regroup, see where we're at, and then write the paper.
Makes sense. I'm with you. So what do you think should be a good time to regroup?
Well, what is, you are, okay, so It's 2 o'clock. It's what, 12 o'clock your time now?
No, I'm on AST, which is 1 hour more than EST. So here the time is 4 o'clock.
Ah, okay. I always thought you're on the other side. I'm sorry. 4 o'clock. So now it's 2 o'clock. So it's 2 hours. We're 2 hours different. Excuse me. What about, is it too late if we can regroup at 11 p.m. your time? Is it too late for you? The only reason is my kids sleep at like 8 o'clock, so I have to be with them. Me and my wife, we get them to sleep, and then after this, or we can do 10:30. What about 10:30? Is that still
11 is good. What I'm gonna do is I'm gonna open the 10:30 one, and I'm gonna leave the meeting open because I'm not gonna do anything else but assignments tonight. So
yeah,
I'm just gonna leave it open and wait for you to get in. And
okay,
so 10:30, and we can keep going as we need to. I work tomorrow, but this
yeah,
is
I worked.
important. So,
Yeah, absolutely. I think we're good to go then.
all right. So I've never recorded myself, so I should hit stop and then save.
Yeah. Now, do you know how to post it as a link, or you don't know how to do that?
So I'm gonna stop now.
Okay.